Hello everyone, thank you so much for your time. So today I want us to look at a very important concept known as continuity. So we want to determine whether a function is continuous at a point. And I would like to stress that limit, as we have studied in the previous episodes, is foundational to the notion of continuity. And then we would move to look at another important concept known as average rate of change. So stay with us even as we explore the journey of continuity and the average rate of change.
Hello, everyone. Thank you so much for the time you've spent with us from up to this time. And today, I would want us to look at a very important point, and that is continuity. And I would like to emphasize that laws, as we have the laws of limit, as we have studied so far, is foundational to continuity, which means that all the principles, the laws regarding limits, we'll be using them as we move along. So please take note. So if, for instance, you have not visited the previous videos, I would advise that you do so that you have a comprehensive understanding of whatever we are doing. Thank you. Now the question is, when do we say a function is continuous at a point? Are there some conditions we have to meet in order for us to say that such a function is continuous at a point? And that is what we are about to start. All right. So a function f, let's call it f. So a function f is continuous at a point, let's call it x equal to if one, the function value exists. If one, the function value exists. So we claim that f of a exists, okay? That is the output exists, which implies that the output at a exists. Two, if the limit of the function exists. So the limit of the function as x approaches a exists. And what is the last condition? Now, the last condition is that the limit of the function, okay, as x approaches a should be the same as the function value. So when these three conditions are met, we claim that such a function is continuous at a point A. I believe we all get it now. So now the question is, can a function be continuous over an interval? Yes, a function is continuous over an interval if it is continuous at each point in that interval. Let me state once again that a function is continuous over an interval if it is continuous at each point in that interval. So please take note. Now, at this point, I would want us to look at an example so that we'll be able to understand the concept really well. So the first example, is a function f given by f of x equal to s squared minus 5, continuous at x equal to 3 pi, or why not? So the question is that is a function f given by f of x equal to x squared minus 5 continuous at x equal to 3? Why or why not? All right. So it means that we have to go through the conditions, right? So we have learned the conditions. So I want us to go through the conditions very quick. So now the first condition is that the function evaluated at the point A must exist. In which case, over here, we have, since the function f of x is defined as squared minus 5, now the first condition is that f evaluated at a point, remember the point over here is 3. So if the function evaluated at point 3 should be what? And that should give us what? 4, right? Now, with the second condition, we need to find the limit of the function as x approaches 3. Right? So it means that limit of the function, and the function in this case is x squared minus 5. Right? And what would that be? But remember, we kind of learned the laws. And so if you have visited our previous videos, we kind of apply the rules or the laws of limit and which law can we use. All right. So over here, straight away, we just plug in the x value. So in which case, wherever we see x, we should replace it by 3. So we're going to have 3 to the power 2 minus 5, which is equal to 4. So at this point, what is the last condition? We said that the limit of the function as x approaches 3 should be the same as the function value, right? Should be the same as the function value. And is that true? Which means that the first condition must be the same. So they are both the same. We claim that, so this implies that f is what? Is continuous. F is continuous at x equal to 3. Good. I believe we all understand this. Good. So let's move to a different example so that we can have an in-depth knowledge of the concept of. So with example 2, so we have the function given by, so the question is the function, so is a function g given by this piecewise function. It is a function. So we want to find out whether this piecewise function or this function g, which is defined by this piecewise, which is defined in a piecewise form, continues at a point x equals to -2. We want to find out whether it is continuous. So it means that we have to go through the same, the same principles or the same conditions. Remember, we have 3 conditions that we have to meet. The first condition is that, what did we say about the first condition? We said that the function evaluated at a point A in this case is -2, must exist. And the second condition is that the limit of the function as x approaches -2 must also exist. And the third point is that the first condition and the second condition must be the same. In other words, the result must be the same. When that is met, then we claim that such a function is indeed continuous at a point -2, right? So let's move on. So what would be g of -2? Just pause the video for a second and answer this question. Now, this is a piecewise function. This is a piecewise function. So which of these two functions should we evaluate? Should we pick as a function for us to evaluate at x equal to -2? Which of the functions should we consider when x equal to -2? Now, it is very important for us to note over here that since we are evaluating the function at 2, in other words, we're evaluating the function at x equal to 2. So we look at the function, the first function is half of x plus 3, but there's a condition. This condition is that x must be strictly less than -2. The second function is that x minus 1, and but it has this condition that has been attached to it. It's x greater or equal to -2, right? So greater or equal to -2, it means that x equal to -2 is found within this range, right? It's found within this inequality. So I want us to take note that we are going to use the second function, okay? So you're going to use x minus 1, okay? So it means that wherever you see x, just replace it by -2, and that gives us -2 minus 1. And that gives us what? -3. Good. Good students. Please, do you all get it? I think at this point, let me explain it once more so that you understand it. Now, the function we are given is a piecewise function, okay? And since we want to find out whether this piecewise function is continuous, the first condition we have to meet is that the function evaluated at the point -2 must exist. But look at the function. Since it's a piecewise function, there are 2 functions there. Look. Now the question is, since we want to evaluate the function at exactly x equal 2, it means that we have to check the conditions that have been attached to the functions. Which of the conditions, okay, can satisfy this or permit us to evaluate the function at exactly x equal to -2? It is the second function, which is x minus 1, because its condition is that x should be greater or equal to -2. Remember, greater or -2 means that x should be what? -2, x can be -2, right? So x greater or equal to -2 means that x can be -2 and some values onwards, okay? So it means that x exists at a function. So I want us to take note. Now let's continue. So with the second condition, we said that the limit of the function must exist. So the limit of the function as x approaches -2 must exist. Now the question is, which of the functions should we use? Remember, x is approaching -2. X is not exactly -2. X is approaching -2. So which function should we use? The first function, because when you look at the condition that is given, it says that x is less than -2, which means that x can approach such a value, but it's not exactly a -2, right? Good. So we're going to have this. Now, when we evaluate this, what do we get? When you evaluate this, what do we get? So it means whenever you see x just replaced by -2, we'll have this. So the answer will be 2. Now, let's go to the third condition. With the third condition, we said that the first condition must be equal to the second condition. But is it a case? What did we get for the first condition? We had -3. And the second condition, we had a value of 2, which means they're not the same. So we claim that since g evaluated at -2 is not equal to the limit of that function, we have that g is not continuous, okay? I hope you all understand this. All right, if you understand this, I want you to pause over here and let's reflect on one or two things. So let's pause the video and let's go over the questions again. Hello, everyone. I would want you to pause your video and try and attempt this question and see what we'll get. All right, so let's see how best we're going to solve this question. We said that for us to solve this question, there are three conditions that we have to meet. Now, the first condition, that h evaluated at a point 3 must exist. Now, which of the function can we pick in order for us to evaluate it? Which of the function? So the first function being x squared minus 9 all divided by x minus 3, and the second function is 7. But then each of these has got a condition attached to that. Now, for us to evaluate the function at a point, it means that x should be equal to what? 3. So this is the condition that relates to this, right? This function, right? So it means that when we evaluate the function at 3, it means that our function would eventually be what? Somebody should give us the answer. That should be what? So what is the, as we evaluate it at 3? Could you pause your video and let's see what we will get, please? So when we evaluate it, we should get what? 7. Good. What about the second condition? The second condition, we said that the limit of the function must exist, right? So the limit of the function as x approaches 3 of the function. So which functions should you pick? So we are going to pick the first function, which is s squared minus 9 all divided by x minus 3, right? Good. Now, how do we solve such a question? How do we do that? So the easiest way is fast. So when you look at the numerator of the function, it's a difference of 2 squared, right? So we can simplify it. And when we do the cancellation, we are going to have x plus 3, right? So it means that wherever we see x, we should replace it by 3, and that should give us what? 6. Good. Now, what did we say about the third condition? So the third condition is that the first condition should be equal to second condition, right? But is it true? Remember, when we evaluated a function at x equal to 3, we had 7. And when we evaluated the limit, we had 6. So since they're not the same, we claim that since they're not the same, we have that f is not what? Sorry, g. It's rather h, sorry. We have the h is not what? Continuous, right? So we have the h is not continuous. All right, so at this point, I think maybe you want to compare your result to what we have here. What did you get? Okay. So I want us to look at the second example and see the third example for today's discussion. So with the third example, we have, it says that let p of x equal to x squared minus 25 out of x minus 5 with a condition that x should never be 5. And then for a constant c for which x is equal to 5. Now the question is, we are to determine c such that p is continuous at x at 5, okay? So we are to determine c such that p is continuous x equal to 5, okay? So we want to determine c such that p is continuous at 5. So this question is a very interesting one, okay? It just has to do with the laws or the conditions that we have to meet. And the first condition, we said that the first condition is that the function being evaluated at a point must exist, right? So let's evaluate p at the point, and the point is what? 5, right? So which value is that? When we evaluate p at 5, what do we have? So we're going to have what? C, right? When x is equal to 5, it is what? The function value is what? Is c, right? Good. How we understand it, right? Good. Now, let's try our best possible to find the limit of the function. Remember, the second condition is that the limit of the function must exist. So the limit as x approaches 5. Now, which function should we use? There's the first function, which is s squared minus 25 out of x minus 5. So when we evaluate it, what do we get? We're going to have what? 5 plus 5, and that is what? 10, right? Now, remember that we said that f is continuous at a point if these three conditions are met. But the last condition is that the function value should be the same as the limit of that function as s approaches 5, right? Should be the same, right? But now the question is, what was the value, since we want to find c, okay? So it says that we should determine c such that p is continuous. So, all right, it has been said that p is continuous, right? And the third condition has to be satisfied. But what did we get for the c? What did we get for c? C, the function being evaluated as at 5 was c. But what about the limit? What did we get for the limit? We had 10. So it means that the value of c is what? Is 10. Please, do we all understand this? The question was that we should determine c such that p is continuous at x equal to 5, right? Good. So remember, we have three conditions to meet. The first condition is that the function p being evaluated at a point must exist, okay? The second condition is that the limit of the function must also exist. Now, the third one is that the third condition is that the function being evaluated at a point should be the same as the limit of the function as x approaching 5, right? But over here, since C said that P is continuous, remember C has it is already been said that P is continuous. So we just have to do is to just play with the rules or the conditions, and that's what we had for this particular problem. So far we've been able to look at continuity, and I believe that with continuity we'll take it serious, because these are some of the questions that could sometimes trick students, especially with the one who has to do with piecewise functions. So I want you to take your time. If, for instance, you cannot understand anything, make sure that you watch the video once more so that you have an in-depth understanding of the concept. I should mention that continuity is a very important concept that you don't want to miss. So please take your time and review them. Today, we've said that a function is continuous to the point A if, one, the function value exists, and that the limit as x approaches A must also exist. We also claim that the function value and the limit are equal, okay? That's what we said. So please take note. And the final message I want to talk about continuity is that if any part of the continuity definition fails, then we claim that the function is discontinuous at s equal to A. Let me restate that. If any part of the continuity definition fails, which is a condition that we stated, okay? If any of them fails, then the function is discontinuous at a point A. Hello, so we are back. I would want us to look at the average rate of change. Now, when we talk of the average rate of change, what are we talking about? If we have outputs values and that of the input with the corresponding inputs, at what point can we talk about the average rate of change, of such change in the output with respect to the change in the input? So we claim that the average rate of the output to that of the to that of the change in input can be expressed as below. Okay, so the average rate of change, we can express it as the average rate of change. Okay, we said that is a ratio of the change in output, okay, to the change in input. Okay, so the average rate of change, we said that is a change in output to the change in input. So I want us to take note. If there's a change from one point in the input to the next point, we claim that the same would to the output, right? So in that case, we can have y2 minus y1 all divided by x2 minus y1. Remember that x2 should not be the same as x1, otherwise such function will not exist. Also, sorry, such condition will not hold, or such equation will not hold. So I want us to take note, okay, that the x2 should never be equal to x1. Otherwise, the average rate of change will not exist. Now, I want to do some illustration so that you have a better view of the average rate of change. Now, suppose I have such a graph. So let me draw a nice graph like this. Let me call this, so x is my input and y as my output, right? Then if I have a curve, okay, if I have a curve like this, then there's a line that passes through such a, let's say there's a line that passes through such a curve, okay? Let me call this point as my point F and this point as my point G, okay? Now, if this is my x1, okay, and then at this point, I call this point my x2. Now, let's look at something really important here. If I plug in the value of x1 into the main function, it means we are going to have what? y1 equal to what? y1 is equal to what? F x1, right? F of x1. And if x2 is being plugged into the main function, we are going to have what? If s2 is being plugged into the main function, we should have y2 equal to f of x2, right? So let's take note. Now, let's look at something really important here. At this point, I can know the change in x and then the change in y, okay? I can know the change in x and the change in y. So over here, let me use a different pencil. So over here, I can know the change in x by just finding the difference, right? So the change in x, for us to know how much x has changed, I just have to know how fast x has changed over time, okay? So the change in x will just be x2 minus what? x1. Okay, good. Now let's look at something really important here. Now, how do I determine the change in the output? So the change in output, I just have to trace this. So this is the point at which I can know the change in the output. So in which case, if I subtract the output, I'm going to have f of x2 minus f of what? x1, right? Good. Now, let me ask this question. What line, if I have a curve, okay, and there's a line that passes through it, but this line, just touches just only 2 points in the curve. What name do you give to such a line that touches a curve at 2 points is called anybody? You can put the answer in the comment section. A line that touches a curve at 2 points is called a secant line. Is a line that touches a curve at 2 points. Okay, so let's take note of that. So by having such a graph or by having such a picture, we would state that the average, so we'll state that the average rate of change, okay, will just be equal to what? F of x2 minus f of, okay, let me say it again. So the average rate of change based on this graph, we're going to have the change in the output, which is going to be f of x2 minus f of x1, all divided by x2 minus x1. So please, let's take note. So that's how we are going to define the average rate of change, which is also the same as what? Y2 minus Y1 over what? X2 minus X1. So let's take note. All right. If you have any question, please put it in the comment section and I will attend to you. All right. So let's get some example. So example will help us to understand the average of change very well. Now, so if I give you a function, let's say for y equal to x squared. Now find the average rate of change as s changes from 1 to 3. What do you think the result will be? So how do you find the average rate of change as x changes from 1 to 3? So what we need to do is that we need to find when x1 is equal to 1, then we find its corresponding, output value. So we claim that solution, so when x is equal to 1, what will be its corresponding output value? And that will give us what? 1 squared, which is 1, right? When x2 is equal to 3, you're going to have what? 3 squared, and that gives us what? 9. So now, which means that the average rate of change, based on the formula, we said that the average rate of change, so the average rate of change will be what? Will be y2 minus y1 or x2 minus x1. What's your y2? Y2 we had what? 9. And your y1 we had what? 1. And the x2 we had what? 3. And the x1 is what? Was 1. Which case we're going to have as our answer. I believe we are all right. Please, if you did not understand it, I want you to probably, put some question in the comment section and I will attend to you on that. All right. So take note, please. Now, I want us to look at a very interesting concept that I did not want you to miss. We term it as a difference question. Okay. So let me state that the average rate of change of x with respect to s is also called the difference quotient. Okay. So note for difference quotient. The average rate of change of f with respect to x is also called the difference quotient. So I believe we are getting it. It's called the difference quotient. Okay. So let's take note. And it is given by f evaluated at x plus h minus f of x all divided by h. But we want to make sure that the h is never 0. But what is this h? Would look at it as illustrated. So let me give you a picture of what I want to say. So if we're in this XY plane, if I draw any curve, so let me draw a very nice curve. If I draw a curve, then a line is drawn such that it passes through the curve. A line is drawn such that it passes through the curve. So let's suppose this is your x1, okay? And this side is your x2. This point is your x2. Now, we can evaluate it. We can evaluate based on x1, we can find f of x2, right? Or f of x1, right? But instead of that, but let's suppose your x1 is just, let's name it as x. So it just means that now, if I decide to add a very small change to x, your x1, let's assume that it is x. If I decide to add something small, a very small number to x, well, let's suppose that x changed by a certain margin, if it changes by a certain margin. So if it changes by a certain margin, it means that this place will just be what x will be equal to what x plus what h. So that small change is what we are calling that what. That small change is what we are referring to as what h. So let's take note. If I have a point, let's call it x, okay? Let's call it x1. But then this x1, we are assuming that it's x. Suppose that there has been a change in x, okay? A change in x. That if there has been a change in x, it means that obviously the x would be affected by a certain margin. But what margin are we talking about? That small change is what we are saying that is your h. So let's take note, okay? So let's suppose it's more or less like, let's say your weight. Suppose that the weight of today, and let's say you just weigh yourself, okay? And then I mean, after some few days, you weigh you check your weight and you realize there has been a change. So that change that has happened is what we refer to as the age. Did you all get it? Good, very good. All right. So we knowing the x, we can find its corresponding output value. Okay, good. Now, knowing your x2, we can find its corresponding value for the output. Okay, so the output over here will just be what? F of what? X plus what? Plus h, because there has been a change in your x2, right? There has been a change. So it means at this point we're going to have x f x, right? And this point we're going to have what? X plus h, and then what? F. You're going to have x plus h, and then the function value will be what? F of what? X plus h. I hope we all get it. And I also want to stress over here that I want to stress on the point that a line that touches a curve at 2 points is known as what? A secant, right? So it means if that's the case, now the question is, what has been the change in the function value? So the change in the function value will just be what? F of what? X plus h minus what? F of x, right? That would be the change in the function value. Now, what about, if that's the case, then what about the x? What do you think will be the change in x? Is what we call the h. Thank you. That's you guys are so smart. That's so good, good, good. All right. So that now we know the difference quotient. Now we know the difference quotient. So with the difference quotient, we claim that the average of change of f with respect to s is also known as the difference quotient. But this time around, we say that there has been a change in the input value. Okay, there has been a change in the input value. So I want you to sort of take note of that. It's a very interesting concept, and we'll solve more examples so you would kind of appreciate it more. All right. So at this point, let's look at some examples. Okay, let's look at some examples, and I think you would like it. So example 1. All right. So for f of x equal to x squared. Now, with this question, we want to find the difference quotient. Okay. All right. So the first problem. So with the first problem, now now we have to, we have to know the formula, and if we said that the formula is what? F of what? X plus h minus f of x all divided by what? H, right? Now, with the first problem, remember the a part, we have bin 5 and h being what? 3. So we just have to do some substitution. But then remember, we have the function, the main function to be equal to what? The f of x to be equal to x squared, right? Now, when x is 3 and when s is 3, so when s is 5 and the h is 3, what do we get? That leaves us what? 8, right? And then the h was given us what? As 3, in which case we're going to have f of 8 minus f of 5, right? But now the question is, what is my function? What is f of 8? If f of x equal to x squared, what is f of 8? It just means that wherever I see x, I should replace it by 8, right? And then I subtract that. I kind of subtract f of 5 from that result, okay? So in that case, we're going to have 8 squared minus what? 5 squared, or divided by 3. That gives us what? 64 minus 25 out of 3 and 10. Good. That's good. I hope you all get it. So let's cut that b part. So with the b part, x has 5 and then the h has 0.1. Okay. So with the same computation, now my x is still 5 and my h is what? 0.1. Okay. Minus my x, which is still this, and then my h 0.1. And that gives us what? F of what? 0.1 minus f of 5, all divided by 0.1. Now, what do you think we will get? So we should get something, when we plug into the main function, we should get 5.1 squared minus 5 squared, all divided by 0.1. So that gives us what? I think when you do your computation, you should get something like 10.1. Okay, all right. So at this point, let me know if you have some questions. All right, so let's move to the next question. Now, the next question is that for f of x equal to x cubed, you have to find a simplified, says that find a simplified form of the difference quotient. Okay. Now, what is the formula that are we going to use? What formula are you going to use? So the same formula, okay? But if I were you, I would just pause the video for a second and try to see if I'll be able to do it. So by the formula that we have, so we have f of x plus h minus f of x all divided by h. Now, just means that wherever I see, so if f of x, remember the main function is f of x equal to x cubed. Now, if I have x plus h, what do? If I have f of x equal to x cubed and I have to find f of x plus h, it just means that wherever I see x, I should replace it by the whole of what? X plus h. Please, do we all get it? So it just means that wherever I see x, I should just replace it by x plus h. It's the same thing over here. So I want us to take note. All right. So over here, we're going to have, just mean wherever I see x, I should replace it by x plus h. So which will give us x plus h cubed minus, remember f of x already x to the power 3, and that gives us something like this. But we have to simplify this, okay? Now, I want us to take note that if I have a plus b all to the power 3, I can expand this as what? A to the power 3, 3a squared b plus 3a b squared plus what? B cubed. So let's take note. Please, let's take note. So we are going to employ the same thing here. So let's take note. All right. So if I'm to expand x plus h to the power cube, it means that I'll just have to apply the same thing here. So I'm going to have x to the power 3, 3x squared h plus 3xh squared plus what? H cubed minus what? All divided by h. So over here, we can simplify, right? We can further simplify. We can do some cancellations. So this s cube cancel this s cube, then we can do some further cancellation. So with this cancel that, so we're going to have 3x squared plus 3xh plus h squared. But then we have to assume that h is never 0. Otherwise, this will not hold. H should never be 0. Otherwise, this would never hold. So I want us to take note of that. Please, are we all getting it? So I want us to take note of that. Okay, so the next question, this is a very nice question. I want us to, take note. So the next example. So if for f of x equal to 3 out of x, you have to find a simplified form of the difference quotient. You have to find a simple form of difference quotient. Now we ask ourselves, what is the difference quotient? So we could pause the video. You could pause the video, then you try to see if you'll be able to do it by yourself. Okay, so let's go by the formula. We said that the f of x plus h minus f of x all divided by h as the difference quotient formula, right? So we have this. So as I mentioned, so if I have to evaluate f of x plus h, it just means that in the main function, wherever I see x, I should replace it by x plus h. Okay, all right. Good. So in the main function, it means that we're going to have what? X all divided by x plus h. Good. Minus, we already know the f of x, which is what? X plus x. Sorry, 3 divided by x, divided by that of what? H. Okay. And so it means this one, we need to simplify it a bit, right? So we need to simplify it. So when we simplify this a bit, we should have something as this, all divided by h. Okay. When we simplify it, we should have to further, when you do some distribution and we further simplify it, we should get something as this, all divided by h. And that should give us minus 3 h, because this should cancel this, right? And that will something as what? X all divided by h. Over here, I want us to take note that in algebra, if I have a divided by 3 also divided by c, what we do, we can reciprocate. Remember, C is over 1, so we can reciprocate C, and that gives us something like that. So we're going to apply the same thing, which means that this H will cancel this, right? So if that's the case, we should have something like -3 on divided by, I want to state that H should never be equal to 0. So let's take note. So if you are given this problem to solve, then we have to take note. Okay, it's not really difficult, but just that with the algebra, we have to be very careful with the algebra so that we don't mess up things. So far, we've been able to look at the average rate of change, and we said that it's a slope of a line between 2 points. Okay, and we said that the average rate of change is a ratio of the change of the output to the change in the input. The line connecting 2 points is called a secant line. Okay, so a line that connects 2 points is called a secant line. So I want you to, take notice of that. It's very important that we know it. And I also want to stress that the difference quotient is the same as the slope formula, and both give the slope of the line between 2 points. Okay, and we also said that the difference quotient gives the average rate of change between 2 points on a graph represented by a secant line. Already we now know what the secant line is. So I want you to take notice of this. Thank you for your audience. Hello, everyone. Thank you so much for your time. Last week, we looked at the average rate of change, which is also known as the difference quotient. Today, I want us to look at difference now using limits of the difference quotient. As a recap, I want us to look at the formula of the difference quotient. So last week, we said that this is the formula of the difference quotient. So it is the function being evaluated at x plus h minus the main function all divided by h. And we said that such an h is what we called a change in the x, okay? And we also claimed that such h should never be 0. Such h should be different from 0. So let's take note. Now, today, I want to draw your attention to something that is very, very important. It applies to life. You see, the problems we are being confronted with in life are nonlinear in nature. What do I mean? So, for instance, if you are having a particular problem, the only way for which we can solve that particular problem is to remove your mindset from that problem, a different area where you can get a solution from. I believe you are getting it. So I want to draw your mindset to something that, suppose I have, so let's look at this graph. So I give you a graph as this graph is not nice. So let's look at this graph. I give you a graph as this. Let's call this X. Let me call this Y. If this is I have a curve as this. So the problems we are confronted with in life is as if it's like a curve as this. Okay. So this is our curve that I'm talking about, of which I said is nonlinear. Okay. So this is a problem we want to solve. But then this is a mindset I want us to have this mindset that for us to solve this curve, we want to make sure that the problem becomes as smooth as this, or in other words, becomes a line as this. So let me call this as my T. Okay, so this is a curve and this is a line. Now, suppose this is a point, let's call this point, let's call it X. So the X value is okay. Now, suppose that initially it has gone through a change where we have X plus H. Remember, I mentioned that it's just a small change that has occurred to X, which means it eventually shift the X value, right? Good. Now, which means that at this point, okay, on the graph, we can find a value there. But the problem is that we want to stretch this curve. It's as if we are holding the end point of the curve and trying to stretch it onto such a time or onto such a point it lies on this tangential line. So this line is tangential in nature, okay? So a curve at a point is called a tangential line, okay? So a line that touches a curve at a point is called a tangential line. So let me write it, a tangential line. Good. Now, as I mentioned, you want to hold the end point of the curve and try to stretch it until such a time it lies linearly on this line. What it means is that for us to do the stretching, what happens is that we have to decrease the h value. So let's decrease the h value. It means that we're going to have x plus h2 over here. Then we decrease it further. Then we come here, we have x plus h1. Then until such a time we get to until such time we get to the x point. Okay, so when that happens, it means that now the distance over here will now goes down, right? The distance over here will now become very small, very infinite. So the point we are going to make is that as the curve is being stretched until such a time it lies on this curve, we're going to have h value to be very, 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 very small. Suppose that our initial h value, which is h3, was, let's say, was 1, okay? So until we get to h1, we would realize that h value would probably approach almost 0, okay? So that is the notion over here. So we are saying that the smaller the distance between, okay, we are seeing that the smaller the distance between the curve and the line, okay, the easier it is for us to solve the problem. So that is what we are trying to do. Now, having understood this, I want us to take this a bit further. Now, let's apply limit to the difference quotient, okay? Now, already we know the difference quotient is being defined this way. Now, if we apply limit to the difference quotient, as h approaches 0, happens? What is happening? So it just means that we eventually become more or less like a line, right? That becomes like the slope of that particular line. Do you all get it? So that becomes like a slope of that particular line. I hope we get it. So eventually this becomes more or less like a slope. So we call this one a slope. And I will also want to say that such a limit is also known as instantaneous rate of change of f of x at x. So let's take note that this is also known as the instantaneous. This is also known as instantaneous rate of change of x, of f of x at what? At x. Good. I hope we all get it. We said it's known as the instantaneous rate of change of f of x at x. Good. I want us to now define it properly. Let's say for a given function, y equal to f of x, okay? Then we claim that a derivative at x is a function defined by f prime of x. So this is how we read it. We said f prime of x equal to the limit as h approaches 0 of x, of the function being evaluated as these values, okay? And we also said that h should never be 0, provided that the limit exists. So let me say that provided that the limit exists, okay? I would also want to kind of state that if f prime of x exists, then we say that if f prime of x exists, then we claim that f is differentiable at x. So let's take note. Now, I want us to look at the first example. So let's get the first example of the day. So with example 1, so for f of x equal to x squared, now find f prime of x using the limit definition. So what is the limit definition? We claim that the limit definition, so f prime of x will be equal to what? Limit as h approaches 0 of x plus h minus f of x, or divided by h. But then we claim that h should never be 0. Good. Now, how do we solve this? How do we continue with this? Now, what we'll do is that, so if I have f of x to be x squared, then it means that if I want to find f x plus h, it just means that wherever I see x, I should replace it by what? X plus h. We looked at that last week, okay? So that means that wherever you see x, we just replace it by x plus h. So we employ the same thing here. So let's go on. So wherever we see x, we replace it by x plus h in the main function. And that gives us what? X plus h, all to the power 2 minus our f of x, but the question is x squared. Good. Now, when we simplify the numerator, when we expand and simplify, we should have x squared plus 2x plus h squared minus what? Minus x squared. So when we look at it, we can do some cancellations, right? When that happens, we're going to have limit as h approaches 0 of 2x plus h squared, all divided by that. But this can better be simplified, right? So which means you're going to have limit as h approaches 0. When you factorize the h out, we should have 2x plus h, all divided by h, right? And this is that. So in which case we should have limit as h approaches 0 of 2x plus h. Now, this is where we also employ one of the laws of limits. So what is straight away, what it means is that wherever you see h, we should just replace it by what? 0, right? Because it's a simple function. So we just plug it there, we have. So it means that anytime we differentiate a function x squared, its derivative is 2x, or its slope is 2x, okay? So derivative is also known as the slope, as we saw that in our illustration. So I want us to take notes, okay? Good. Now, find this. What if I want to find f prime of minus 3 and f prime of minus 4, or the differentiated function being evaluated at negative 3 and that of negative 4, okay? So when that happens, it means that wherever I see x in the f prime of x, as we just replace it by minus 3, right? So we have f prime of x being equal to 2x. So now what is f prime of f of the differentiation function being evaluated in negative 3? Means that I will have something like this. So you can do the same for the second problem, right? You can do the same for the function being evaluated at negative 4. So let's look at, so with example 2, let's look at a situation. Now I want us to look at it. What if that this time around my f of x is a cubic function? How do I find f prime of x using the limit definition? So we go through the same procedure. Okay, good. So if I have such a function, then it means that by using the limit definition, f prime of x will just be equal to the limit as h approaches 0 of f of x plus h minus f of x, all divided by h. So using the same principle, which means that by simplifying, we should have something like x plus h to the power 3 minus what? S to the power 3, all divided by h, right? Now, last time we kind of solved a similar example, so I would go straight to the point. Now, by simplifying the expression under the cube, happens that when we expand, we should have something as this. So I explained the last time. So I want you to, if you have any problem with this, you want to visit the previous content, and I think you will be able to get it. Then we can simplify this a bit, and that should give us what? We can pull out the h. So over here, we can do some cancellation. Then we kind of pull out the h out, and when h is pulled out, we should have some as this, right? At this point, we can still do some cancellation, which means that we said that the limit of a sum, we claim that, remember, this is what we said, that the limit of the sum, as one of the laws of limit, we said that the limit of the sum is the what? Is a sum of the limit. So take notes. All right. So when we plug in wherever you see h, we should just plug in 0. Now, when we plug in now over here in the first function, we don't see h there. What it means is that this is just a constant. If h is not found here, and this just means that h is this 3x squared is just a constant. And we said that the limit of a constant, we said is a what? It's a constant, right? So this means that over here we should have 3x squared. Right? And over here, when you plug in here, it runs to 0 because h is 0 here. Also, h runs to 0. Okay. So in that case, you're going to have only 3x squared, which means that anytime we differentiate x to the power cube, we should have 3x squared. Okay. Good. I believe we are all getting it. So if I derivative has to find f prime being evaluated at 1, what it means is that, so this implies that wherever I see x, I should just replace it by 1. Okay. And that gives us something like this. I believe we are all getting it. Are we following? Good. If you have any questions, please put it in the comment section and I would inspect it. So I want us to solve one more example, okay? I want us to solve one more example. Then we kind of look at other interesting stuff. If I give you f prime of x and then the b, you want to find f prime being evaluated at 2. Then the C part, I want us to find an equation of the tangent line to the curve at x equal to 2. So at this point, I want you to pause the video and attempt this question. All right, so I believe you have your result. So let's see what we are going to get now that you have your result. Now let's compare your result to what we have here. All right, so we have f of x being equal to 3 or divided by x. Now, using the limit definition, it means that f prime of x, which is also known as the slope, is equal to limit as h approaches 0 of f x or plus h minus f of x divided by h, but then we said that h should never be 0. All right, now what we do is that wherever we see x, we just replace it by, in the first case, we have f x plus f of x plus h. Okay, so in that case, you should have something as this. And then for f of x, already we know the value of f of x. Okay, we know the function, so that is what 3 on x, or divided by h. Okay, so let's take note. Now, it just means that over here, we just have to simplify. And when we simplify this, what do we get? We should have something like this, all divided by h. Then when we go further to simplify this, we should have all divided by h. Okay, now let's simplify this a bit. And when we simplify this a bit, we should, because over here, there will be some cancellation. So we should be able to have something like this. Now all divided by h. But last week, I explained something. So this will cancel this by algebraic manipulation. We claim that a divided by b, let me use a different pencil. So a divided by b divided by c, okay, can be written as this. We said that we can reciprocate the c, and that gives us what? 1 over c. So it's the same thing over here. So when you apply the same thing here, you should get that. Okay, good. So let's take note. So when that happens, you should have limit as h approaches 0 of minus 3 on x plus h. Now, what did we say? This is in the previous episode, we said that the limit of a quotient is a what? Is a quotient of the limit. So the limit of the quotient is a quotient of the limit. So take note. So now, what is the limit of the function minus 3 over the limit as h approaches 0 of x plus h? Now, what is the limit of minus 3? The limit of a constant, we said, is a what? It's a constant, right? So the limit of a constant is a constant. And when you look at the denominator, it just means that wherever you see h, you just replace by 0, and that happens, you have something like what? X squared. Let's take note. So when we simplify this, we should have something as this. Okay, for the first derivative, we should have something as this. Now let's go to the B part of the problem. The B part of the problem says that we should evaluate the differentiated function at 2. Okay, so that's the B part. The B part says that you should evaluate the differentiated function at 2. So which means that wherever I see x, I should place it by 2, and that should give us what? Minus 3 on 4. Now C, the C part, we are told to find an equation of the tangent line to the curve at x equal to 2. Find the equation of the tangent line to the curve at x equal to 2. So this is a very interesting question. I believe that this in every year, this the kind of questions I give to my students, and sometimes when they see questions like that, they fumble, because it requires that you know the difference quotient. It requires that you know how best to find certain things before you attempt this question. So if you don't know how to find the first problem, it means that you may not be able to attempt this. So this is an opportunity for us to learn something that we can hold on to anytime we are called on to produce the results. So I want us to take note. All right. So for C, now we said something about the tangent line. So the tangent line is just like the normal simple line. The number, it is y equal to mx plus c. And the m is known as what? The slope. Okay. And the c is just the what we call the y-intercept. Okay. So let's take note. All right. So already we know our m. What's m is the slope. It has already been evaluated, which is what? Minus 3, 4. Okay. So our m, already we know our m is what we call the f prime. Okay. The f prime is also known as the slope. Our m already we know, which is already been evaluated at -3. So let me state that x equal to 2, our m is equal to what? Minus 3 on 4. So let's take note. Now, it means that we have to find our y. Okay, how do we find our y? If you know your x, how do you find y? So already we know the main function. So our y is also the same as this, right? Our y is also defined as what? F of x. Our y is the main function. So which implies that our y should be equal to what? F being evaluated at 2. But what's our main function was what? Main function, let me write it here, was what? 3 on x. Okay. So now if we evaluate this function at 2, we should have something as this, right? Now, the point of this, the whole point is to try to find C, okay? Good. Now, we have to plug all of this back into this equation, okay? So now by plugging in
into the main equation, we should have something like 3 on 2 equal to, what is our m? We know is this. What is our x? Our x is 2. Now, this will help us to find our c. I hope we are all getting it. Now, when we simplify, you should have c to be equal to what? Who can guess the answer for c? Our c should be what? Should be 3. Good. When we simplify, our c should be 3. Good. Now, when you plug it back, so this implies that mine should be what? Because now we know our m should be what? Minus 3 on 4x plus c. Our c is what? 3. So this is the line to the curve this is a tangent line to the curve at x equal to 2. So let's take note. I hope at this point we are getting it, right? This part I would want to kind of emphasize that this is an interesting section that I believe you will not want to miss. It is very interesting. You may want to understand all of these things because these are, applicable to real world situations. And I would at some point I will bring in an example that is relatable. Okay, so please take note even as we explore such journey. Now, at this point, I want us to look at a very interesting thing. Now, is there a function such that is not differentiable? Is there a point in a function such that is not differentiable? Or that situation? Are there some situations, where a function may not be? So that's when at this point us to look at it. Okay. Now, one of the first conditions for which a function may not be differentiable is this: if there is a corner, okay, if there's that what we call a caps. If there's a caps or a corner in a curve, it just means, or in a function, it just means that such a function is not differentiable at that point. So I want us to take note. If there's a corner or what we call caps, okay, if there's a corner or what we call caps, it means that the function may not be differentiable at that particular point. So let me do some few drawings. So let's look at a curve as this. So I have something as this, and A is defined here. Now, over here, for example, when you trace the A down, because this is a corner, we claim that A will not be differentiable at this point. A will not be differentiable at this point. Sorry, the function will not be differentiable at A. Please, are we getting it? If we have a curve like this, it's just because there's a corner here or a caps over here, it just means that the function will not be defined at the point A. So let's take note. Another example is a function, a graph as this. So let me define it this way. So I have a curve as this, then something as this. Over here, we claim that for instance, if I trace it down here, it just means that A will not be differentiable at such a point, okay? Because this point is a corner, it just means that the function will not be different at the point A. Please, are we all getting it? Good. So I want us to take note that for as long as there's a corner or what you call a caps, it just means that the function will not be differentiable at that point. So let's take note. And the last example for the illustration will be a graph as this, and I come this way, I have a point here, I have another point here. So the graph will not be differentiable at A1, also will not be the function will not be differentiable at A2 because these are all caps. So let's take note. These are very interesting things that I believe that they are crucial and you don't want to miss them. If you have studied calculus and you do not know this, it means that there's a loophole that you have to fill. And these are some of the things that you don't want to miss. It's very, very important. So please, let's take note. Another condition that I want us to consider is when there's a vertical tangent at A. So I'll write that a function f of x is not differentiable at a point x equal to A if there's a vertical line, okay? If there's a vertical tangent at A. So let's take note, please. Let's take note. So if I have a graph as this, let me see if I'll be able to give a simple graph. I have something like this, okay? Then I have a tangent line as this, such that I have a tangent, vertical tangent that passes through such a point. We claim that such a graph or such a function, the graph of that function will not be differentiable at the point A. So I want us to take note, okay? That is very, very, very important. So this is a vertical line, okay? So this is the vertical line, okay? So we claim that such a graph would not be differentiable at the point A. So please, I want us to take note. Please, let's take note. And then the last condition that I want us to consider
is that a function is not differentiable at a point s equal to a. A function is not differentiable if it's not continuous. Okay, so let me write it down for you guys, that a function f of x, okay, is not differentiable at a point x equal to a if it is not continuous. Okay, let me stress on this, that if it's not continuous at, so let's take note, please. All right, so let me give a graph for us to understand this. So if I give you a graph as this, let me think this graph is not that interesting. So let me give you this graph. Let's give a graph as this. So if I have this graph, let me bring another graph. I kind of use this. So this is, let me deepen this so we all can see it. Then if this is minus 2, so if this is minus 2, 1, can we say that g of x, if this is g, if such graph is g, okay, can we say that g is continuous at minus 2? Please pause the video and let's see whether we can answer this question. The question is g continuous at x equal to minus 2? Is g continuous? The answer is what? No. It's not continuous because there's a what? This whole, the whole over here, the whole we see here, the whole above minus 2 means that the whole over here, the whole above minus 2 means that there's a what? It just means there's a discontinuous at that point. So it means not continuous. So if it is not continuous, it means that if it's not continuous at negative 2, it just means that it's not differentiable. So I want us to take note. So these are some fundamental, stuff that you may not want to miss. So please, let's take note, please. It's very important that we understand such things. Now, if you think you have understood this, I want us to look at this problem. Let's see whether you really understood the principles or the conditions I just gave. So if I ask you this question, let's say, then I ask you this question: where is f of x equal to such absolute function not differentiable, and why? So let's pause the video, then we try and attempt this question. Let's pause the video, then we attempt this question. All right, let's move on. Now, what can we say this function is not continuous at? So our f of x differential at 6. Good. So we see that this function is not differentiable at x equal to 6. Why? So the easiest way for us to look at it is to draw the graph of this absolute function. If you draw this graph, you will see that the graph of this function will just be something as this, right? What did we say? Remember, there's a corner over here. And because there's a corner at 6, it just means that the function is not, such absolute function is not what differential. Do you see that? Because there's a corner at 6, okay? There's a corner at a point 6. It just means that such a function will not be different. Okay, so let's take note, because there's a corner at 6. That is why this function is not differentiable. I believe you all get it. Please, I would want to, send, subscribe, like, turn on your notification button so that anytime I upload my content, you will be the first to have access to it. Once again, please again, share the videos to your colleagues, loved ones, and I believe that this video will be a blessing to you all. Thank you so much for your time, guys.